To illustrate the concepts related to the application of VAR models, we will use an example dataset consisting of 4 macroeconomic indicators on the Canadian economy. The dataset is called Canada and is available in the VARs package in R. The Canada dataset includes data on 4 macroeconomic variables from the first quarter of 1980 to the fourth quarter of the year 2000, that is, it is a quarterly dataset consisting of 84 observations. The variables in the dataset are employment, labor productivity, real wages, and unemployment rate. If we want to include all 4 of these variables in the VAR model, then we will have 4 endogenous variables, or k equals 4. First, we must focus on the deterministic terms that we want to consider in the VAR model. Sometimes, we can make the decisions about deterministic terms based on theoretical considerations about the variables. For example, macroeconomic variables such as GDP usually have a deterministic trend, so we often include a trend component when dealing with variables such as GDP. Another example we can consider is that of interest rates. Interest rates generally do not have a trend, therefore, we often include only a constant if our VAR model is dealing with just interest rates. To decide on the deterministic terms, we can also plot the variables in the dataset. This can give us a lot of information about the constant, trend, or seasonal adjustments that we might need to consider in the model. Let us take a look at the plots of all the variables in the Canada dataset we are considering. The employment, real wages, and labor productivity have a strong upward slope with time. The unemployment rate does not show any indication of a deterministic trend. Overall, this indicates that including a linear trend in our VAR model might be a good idea because some of the variables seem to be trending upwards. Moreover, we should include a constant or intercept in the VAR model. The reason behind this choice is that all the 4 variables indicate a non-zero mean. We exclude the constant only if the variables are stationary around a zero mean. It is important to note that the choice of trend and constant will change if we decided to estimate a VAR in differences. If we take a first difference of a linearly trending time series, it will remove the linear trend component and leave only a constant. Therefore, we do not include a trend in the VAR model in first differences if the original series show a linear trend, and we only include a constant or intercept. Suppose the original time series show a quadratic type of trend instead of a linear trend. In that case, we include a linear trend component in the VAR model in first differences. This is because taking first difference of variables will not entirely remove the trend. We will still be left with a linear trend after taking the first difference of a quadratic trend. If we end up using the second differences in the VAR model, it will eliminate the quadratic trend and we will only need to include a constant in the VAR in second differences. In our example, some of the original variables seem to be trending. The trend is linear and not quadratic in nature. So we are inclined to include a linear trend and constant in the VAR model. If we wanted to estimate a VAR in first differences, then we would only need a constant because taking first differences of variables will remove the linear trend. Moreover, we do not need to consider seasonal adjustment in our example. If there is seasonality, we usually see cyclical pattern with clear frequency as shown in the example plot here. If we look at all the plots of our variables in the Canada dataset, none of the variables show any seasonal patterns or seasonality. When estimating a VAR model, choosing the lag length is one of the most important decisions that we must make. The lag length should be large enough to avoid any autocorrelation of the residuals, but we must also avoid including too many or unnecessary lags. One of the most commonly used methods to decide the lag length is the information criteria. Akaika's information criteria, Schwartz information criteria, and Hannon-Quinn information criteria are the most commonly used for this purpose. The AIC and SIC formulas shown here are general formulas applied in case of univariate OLS models and are useful in understanding their structure and logic. K is the number of parameters included in the model and N is the number of observations. We choose the model that minimizes the AIC, SIC, or other information criteria we are using. If we include more variables in a model, K increases and the value of AIC and SIC will also increase. That is, these information criteria impose a penalty on including more variables and parameters. If the variables are important, then RSS will decrease and compensate for the penalty. Hence, the overall AIC or SIC will fall if the variables are important. However, if the variables and parameters are unnecessary, then RSS will not decrease while K will increase. This will increase the value of the information criteria. We will know that the variables are unnecessary because the AIC and SIC will not be minimum. In case of multivariate models such as the VAR and VECM, we cannot use the general univariate formulas for AIC and SIC. Instead, we adjust these formulas for the VAR and VECM models as shown here. These formulas represent the Lutt-Pohl's version of information criteria for VAR and VECM models. Sigma cap n is the estimated variance-covariance matrix of the VAR model with lag length n. The term containing nk square imposes a penalty on including extra lags in the VAR model. In case of VAR and VECM, we use these information criteria to decide the lag length. We estimate the AIC, SIC or HQIC at different lag lengths and choose the lag length that minimizes these criteria. In R, we can use the VARSelect function provided by the VARs package for lag length selection. The VARSelect function automatically estimates the Lutt-Pohl's version of information criteria including the AIC, SIC and HQIC for different lag lengths for the VAR model. In the command shown here, we first input Canada, which contains the dataset with our 4 variables under consideration. The lag.max option is used to specify the maximum number of lags to consider for estimating the information criteria. Lag.max equals 8 means that the function will estimate information criteria for up to 8 lags in the VAR model. The results will, therefore, include information criteria for VAR with lag 1, lag 2, lag 3 and up to lag 8. Then, we can choose the lag length that minimizes the AIC, SIC or HQIC. The option type can be used to specify the constant or trend that we want to include in the VAR model. Type equals both means that we are including both a constant and a trend in the VAR model. Additionally, we can specify type equals trend for trend only, type equals const for constant only or type equals none for a VAR model without constant and trend. The season option can be used to specify and include seasonal dummies in the VAR model. We do not need to create any seasonal dummy variables ourselves, we simply need to input the frequency or length of the seasonal period. The function will automatically create and include centered seasonal dummies. For example, the Canada dataset is quarterly, so we can specify season equals 4 if we wanted to include quarterly seasonal dummies. Similarly, we can specify season equals 12 for monthly data to include monthly seasonal dummies. Apart from these, we can also include exogenous variables in the VAR model using the exogen option in this VARSelect function. In Stata, we can use the VARSOC command to estimate the information criteria for different lag lengths of the VAR model. In the VARSOC command, we first specify all the variables we are considering in our VAR model, which include E for employment, PROD for labor productivity, RW for real wages, and U for unemployment rate. The max lag option is similar to the lag.max option in VARSelect. We specify max lag 8 to consider up to 8 lags in the VAR model and estimate the information criteria for all lags up to 8. The exog option can be used to specify any exogenous variables we are considering in the VAR model. We have specified exog t to include a trend in the VAR model. Stata does not give us a separate option to specify and include trend in the VAR model. However, if we want to include a deterministic trend, we can do so using the exog option as shown here. The variable t is simply the time ID which we have specified in the exog option. The option LUTSTATS is specified to estimate the Lutt-Pohl's version of the information criteria. We estimated the Lutt-Pohl's version in the VARSelect function in R as well. The table here shows the recommended lag lengths for the VAR model in the case of our Canada dataset example. As we can see, we have included several different VAR specifications to estimate the AIC, SIC, and HQIC. Earlier, the plots of our variables indicated that we should consider a constant and trend in the VAR model. In the VAR model with both constant and trend, most of the information criteria indicate towards a lag length of 2. HQIC recommends a VAR 2 in both cases of 8 and 4 maximum lags. On the other hand, SIC recommends VAR 2 when we specified maximum lags as 4 while estimating the information criteria. When we specify a VAR with only constant or a VAR without constant or trend, most of the information criteria still indicate towards a VAR 2 model. As a result, we are inclined to include 2 lags in the VAR model. It is important to note that lag length selection using information criteria is not foolproof. There are several things that we must keep in mind when using or estimating information criteria for lag length selection in VAR. When we choose lag length using information criteria, it is still possible that the VAR model residuals end up being autocorrelated. After estimating a VAR model, we must apply goodness of fit statistics to ensure that the residuals are not autocorrelated. If we observe autocorrelation in VAR residuals, then we must increase the lag length of the VAR model beyond what is recommended by information criteria to eliminate autocorrelation. In case of VAR and VECM models, we generally do not rely on AIC or ACICA's information criteria. This is because AIC has been observed to asymptotically overestimate the lag length in VAR and VECM models, whereas SIC and HQIC give relatively consistent results. Hence, we generally rely more on SIC and HQIC. The choice of maximum lags while estimating information criteria can also influence the results. The maximum lag should not be so small that it ends up being less than the true lag order. On the other hand, the maximum lag must not be too large because it reduces the number of observations. This is because the pre-sample observations to be set aside for estimating VAR depends on the chosen maximum lag order. For example, if maximum lag is 40, first 40 observations will be set aside as pre-sample even for a VAR 1 model while estimating information criteria. This potentially causes a lot of information loss and may affect the results. In our example, we used maximum lag as 4 and 8 while estimating the information criteria. The reason behind that is that we are dealing with quarterly data. It is generally recommended to include at least one seasonal cycle as maximum lag or use multiples of the length of the cycle. We are dealing with quarterly data, which gives us a length of 4 for the seasonal cycle. Hence, we used 4 and its multiple 8 as maximum lag. Thank you for watching and I will see you in the next tutorial.